Hi, experimental psych students. We're going to jump right into Unit 1 material. Unit 1 it's a review of research methods and some statistics. Experimental psych is the third in a three-course sequence with psychological statistics, research methods, and now experimental psych. So really this should be a review. This is stuff that you should have already gotten out of those previous classes, but I'm just trying to refresh your memory. Some of the stuff might be new for at least some of you. And when we get to some of the statistics stuff, it might be new for most or even all of you. Or maybe you had me and we actually went over some of the exact same slides you're going to be seeing in this review with the statistics. So what the hell am I doing here? What the hell are you doing here? You're a psychology major. Research methods and statistics are very important for a psychology major. I teach this class because I think they're the most important thing that students get out of a psychology major. Some of you won't go into psychology. You might remember some of the content from some of the interesting classes that you take, and that's great. That's probably what most people were most interested in. But in terms of critical thinking, I think research methods and statistics are actually the most important classes for students. More specifically to psychology, in terms of what are you doing here? Well, experimental psych, it's kind of a weird class. Some schools don't have this class. Some schools would call this just the lab of research methods. So why do we need research methods? And our answer is going to be to answer interesting questions, which is what scientific psychologists want to do. You need to test scientifically. You need to test your ideas. Why do we need statistics then? Another big piece of this class. Well, research methods and statistics match up. To test your ideas with research methods, you're going to need data. Usually quantitative data that we would analyze statistically to find things out, to answer our questions. There are certain types of statistics that match up with certain types of research methods that are appropriate to use with certain research methods. And coming out of at least a graduate program in psychology, you've absolutely got to know which kind of statistics to use in which kind of research situation. But as undergraduates, we also are trying to get you to understand that. First thing I want to review is just the overall scientific process, the research process. Here you're seeing the 5 steps, what are said to be the 5 steps of the scientific research process. Starting from the top, that's step 1, 2, 3, 4, and 5. So the orange rectangles are the actual steps. The arrows over to these blue rectangles are more specific things that you would have to do at each one of those steps. So let's start from the top. The initial observation stage. The initial observation stage, this is not where you're testing ideas. This is really just where you're getting ideas. You're coming up with questions that you think need to be answered. It's called the initial observation because when you think about it, when you come up with a new idea, at one point or another, it probably had something to do with some kind of observation that you made. It might have been something that you've seen. It might have been something that you've heard or heard about. Maybe someone told you something. But if they told you about something, then presumably maybe they observed something. So at some point, somebody observed something. That's why it's kind of called the initial observation stage. Coming up with a question you think needs answering. So you find something that you think needs explaining. Again, the idea for the question could come from pretty much anywhere. This is a hard thing to describe. A lot of students want to know, well, where do you come up with ideas? Well, I can't really explain that very well because ideas can come from pretty much anywhere. It can come from just observing things out there in the world, observing the real world out there, watching people do things, people watching out at the mall or wherever. I think probably the most common thing in psychology or probably in most sciences, ideas often come from reading the previous research that other people have done. So being able to find research articles that are reporting primary research that people did. We'll talk more about how to find those articles later in the class. But I really think that's one of the primary ways that people come up with new ideas to do research, to do new experiments, is by reading previous research, thinking carefully about them, and thinking about, well, what doesn't this explain, or where might there be some holes in this, or what else would this theory predict? So they don't necessarily reinvent the wheel with each new study. You wouldn't want to do that. You take already existing theories, and maybe you tweak the theories, or maybe you think carefully about what else do those theories predict about some other phenomenon, and you go out and test that. Other ideas might just come from talking to other people, like I said before. Maybe someone else says something about the way people are. Maybe that gives you an idea. So again, I can't totally explain how you get an idea. It pops in your head. It's really an unconscious process, so it's not exactly an easy thing to talk about. Just thinking carefully about some pattern of behavior that you notice, or hear about, or know about. So again, ideas can come from pretty much anywhere. To give you a real research example, you're looking at a common mole rat. An animal behaviorist observed that common mole rats exhibit aggression in response to what they eventually found out were strangers. So at least eventually this behavior was labeled xenophobia. Phobia meaning fear. Xenophobia means fear of strangers. It's aggression towards strangers. So you're looking at an aggressive stance. He's saying, step the hell off, stranger mole rat. So that was just step one, just initial observation, getting a research question, an idea for research, something you think needs explaining. From that initial observation, you might generate a theory. It might be too early to generate a theory, but we'll say that you're gonna come up with an explanation for that behavior that you observed. So animal behaviorists observed this xenophobia, and they wanted to come up with an explanation of why they exhibit that xenophobia. What's in it for the common mole rats to be fearful of strangers, to act aggressive towards strangers? So this arrow right here, really it represents thinking very carefully about what causal explanation could explain why this behavior, explain these observations basically. So with the common mole rat example, what causal theory could explain when common mole rats are going to be most aggressive? So really, by definition, a theory, if you want a simple two-word definition, you could say that a theory is a causal explanation. We certainly could give a longer definition that a textbook would typically give, but when you really think about it, a theory in psychology is going to explain some behavior or set of behaviors or pattern of behaviors. And the only way, as far as I can tell, the only way that humans have to explain why something happened is to refer to at least some notion of causal stuff or causes of the behavior. So a theory is really a causal explanation. I'll give you a longer definition in a second. So you've observed some phenomenon you think needs explaining. You've thought very carefully about what could possibly explain this behavior. So your theory is an explanation meant to explain your initial observations. It's also meant to explain other things. Any good scientific theory is going to make at least one specific prediction, and really it should make a bunch of predictions. The relationship between a theory and a hypothesis is that a theory is a broad explanation, a broad causal explanation. It should lead to multiple, more specific hypotheses about what we should be able to see in a certain situation, for example. So this arrow here, going from theory to hypothesis, really just represents deep thinking. You're going to think very, very carefully and logically. If this theory is correct, if it were absolutely correct, what does it predict? A hypothesis, what's the definition of a hypothesis? In high school, in grade school, they'd probably say an educated guess. That definition is not good enough for me. It's not just a guess. Thinking about the steps of the research process, a hypothesis is logically derived from a theory, at least in the best case scenario. It comes from a theory. Ideally, you're not just testing something out just to see. At least if you already have a well-developed theory, you don't want to do that. You want to test a specific prediction to test this idea to see if it's useful. So you're thinking very carefully, if my theory were correct, what exactly does it predict? Ideally, you want to come up with hypotheses that, if they were incorrect, would show that your theory is wrong. So a hypothesis is a specific prediction derived from a more general theory. So you generate a hypothesis. To do that, you're going to have to identify variables that you're going to have to test out somehow. Once you have at least one, preferably more than one, multiple hypotheses, you're going to, again, these arrows down really represent thinking very carefully. You're going to take that specific hypothesis, that specific prediction, and set out to actually test it. Collect data, maybe set up an experiment to test that specific prediction. Or if you're doing a correlational study or quasi-experiment, you're going to go out and find a little piece of the world that's already set up in such a way that can help you test your specific prediction. You're going to go collect data to test that prediction. Eventually, all you have is a set of numbers. After you collect the data, you make observations. Presumably, this is going to be a quantitative study, which is all we're talking about in this class. In the end, all you have is a set of numbers. You'll see later in the class, we'll be using Microsoft Excel, and all we're going to have is columns of numbers. And those numbers are meant to represent the observations. But you don't have any observations when you do the actual analysis, the statistical test of things. You just have numbers. So those numbers need to represent the variables they're supposed to represent in a pretty accurate way if you're validly testing your idea. So this last step represents the statistical analysis, finding results. Now this arrow right here goes back up to the generating theory part. Your idea might be confirmed or disconfirmed. If it's confirmed, that doesn't prove your theory with a capital P. You don't never know for sure that it's true. But potentially you could show that your theory is wrong. If your hypotheses are repeatedly incorrect, if the predictions from your theory are repeatedly inaccurate, well, then your theory is wrong. Get rid of it or modify it so that it can account for what you observe. Back to our mole rats example. Again, the animal behaviorist observed initial observation that common mole rats commonly exhibit aggression towards strangers, now known as xenophobia, fear of strangers. We've already talked about steps 2 and 3, generating a theory, generating a causal explanation, and thinking very carefully, if my causal explanation were correct, what predictions does it make? What hypotheses can I derive from it? Here's a longer definition of a theory. It's a hypothesized general principle or set of principles that explains known findings about a topic and from which new hypotheses can be generated. Shorter way to say it, like I've been saying, it's a causal explanation from which you can derive new hypotheses, generate new predictions. So a pretty informal thing you could say was the theory behind what they tested with the mole rats is maybe common mole rats are going to be particularly xenophobic when resources are scarce and strangers might take them. Really, the theory here is that strangers represent a threat to your resources. Maybe the adaptive function of xenophobia in mole rats is to protect food resources and maybe mates as well. So a hypothesis, again, it's defined here as a specific prediction, usually generated from a theory, logically derived from a theory. Two predictions came out from that thinking that the purpose of xenophobia is to protect precious resources, limited resources. First prediction is that in areas where food resources are scarce, such as dry areas that have much less rain and hence it depletes their food resources, common mole rats will exhibit more xenophobia toward the strangers. In other words, where resources are scarce, they become even more important, so there's going to be more aggression towards strangers to protect those limited resources. And a second hypothesis, a second prediction, was that maybe they won't be as xenophobic to members of the opposite sex on average, because opposite sex individuals aren't just a threat to your resources, they themselves can be considered resources from an animal behavior kind of perspective. They represent potential mates. So they may be a threat to resources, but they're also a potential resource themselves. Lying at the core of what it means to be a scientific theory is that hypotheses and relatedly theories need to be falsifiable. Karl Popper, really, I'd say historically, probably the most famous philosopher of science, emphasized that falsification was kind of like the essence of what it meant to be doing science. It's the act of potentially disproving a theory or hypothesis. So for something to really be a scientific theory, the idea has to make, again, specific predictions like we've been talking about that could potentially be shown to be wrong. There has to be some sort of observation that would convince you that you're wrong for it to be a scientific theory. Some sort of observation that would logically show that your theory can't be accurate because its predictions are inaccurate. So good scientific thinkers should constantly be trying to disprove rather than prove, at least ideally. I'm not saying that scientists always go out setting out to try to disprove their own ideas. But if you don't subject your ideas to tests that could disprove them, other people surely will. So at least collectively, science advances by potentially disproving ideas and coming up with better ideas that account for things better. But logically, proving a theory absolutely true, it's impossible. It's logically impossible. That's why Popper has emphasized falsification as being kind of the more important thing. Theories certainly don't have to be provable, because actually none of them can be proven, but they have to be potentially falsifiable. And the more easily falsifiable, the better. The better the theory. The way to make a theory more easily falsifiable is by developing a theory that makes even more specific predictions. To give you an example, Keith Stanovich talks about this example in his book, How to Think Straight About Psychology. He calls it the theory of knocking rhythms. Just a hypothetical example. It's a silly example, but it's a great example for illustrating this idea of the specificity of predictions makes a theory more falsifiable. Imagine, let's say we're in a classroom, and I can't see outside the classroom door. And I tell you, I have a theory of knocking rhythms. And I say, the next person that comes to the door, I can tell certain characteristics about that person based on the rhythm of how they knock. So someone comes to the door, knocks on the door, I listen to the rhythm of the knock, and I say, okay, based on that knock, that's a male, that's a man. Open up the door, sure enough, it's a man. How impressed are you? You really shouldn't be that impressed. It was a roughly 50-50 shot for man versus woman, and I got it right. It's not totally bad, but you shouldn't be that impressed. Could have been just random chance. Let's say I do the same thing 10 times in a row, and each time I get it correct. I judge the sex of the person correct 10 times in a row. How impressed are you? You should be a little more impressed. The quantity of the predictions was accurate 10 times in a row, so it's higher than it was before. It's more impressive. But let's say I get more specific about my predictions. Let's say that next person that comes to the door, based on their knock, I say, okay, that's a man who's over 6'4". He has brown hair, blue eyes, and he's holding a coffee cup in his left hand. You open up the door, and sure enough, all those predictions are accurate. How impressed are you? You should be really impressed. I made very specific predictions, and they were all accurate. If I did that kind of thing 10 times in a row, you should be highly, highly, highly impressed. That's what I mean and the reason you should be highly impressed is that I've put my theory at a greater risk of being shown to be wrong, a greater risk of falsification, yet it wasn't. That's what it means to have specific predictions that are repeatedly accurate. And that's why the more specific the predictions, the more easily falsifiable a theory is. And it's a better theory. So, ideally, scientists put ideas at risk of being shown to be wrong. And that lies at the core of what it means to be doing science. If you're doing something that couldn't show that you're wrong ever, you're not really doing science. You're just kind of confirming what you already believed. So scientists put their ideas at risk of being falsified, of being wrong. Something that I emphasize in my methods class, and I'm trying to emphasize a little bit in this class, is trying to get you to recognize science versus pseudoscience. Or you could loosely call pseudoscience bullshit. And that's roughly what Neil deGrasse Tyson is saying here. He says to be scientifically literate, which is what I'm really trying to get my students to be, is more scientifically literate, is to empower yourself to know when someone else is full of bullshit. This is just a little true-false set of questions that I want you to actually listen to and answer on your own as I go through them. And it's just kind of meant to get you thinking about why, even if you don't want to do something that you think is very sciencey, that this class and research methods are very relevant to things like clinical psychology, counseling, forensic psychology, and the other helping professions, I would say. So true or false, graduate training, getting a master's degree, even more so a PhD or a PsyD, some kind of doctorate, enhances people's subjective ability to judge whether someone is suicidal. Or, if you're a forensic psychologist, for example, or maybe a clinical psychologist, whether a convicted criminal is likely to commit crimes again. True or false? Graduate training helps you to be able to predict those things based on your subjective judgment. Based on evidence, the answer is false. Whether you have a master's or a doctorate, it looks like people don't get better at judging whether someone's suicidal, and they don't get better judging whether some convicted criminal is likely to commit crimes again in the future. Based on data, you don't get better with that with graduate training. True or false? Extensive experience as a clinical psychologist enhances one's subjective ability to judge whether someone's suicidal. Same things as before. So judge whether someone's suicidal or whether a convicted criminal is likely to commit crimes again. So we've said that graduate training doesn't increase this subjective ability. Does, decades of experience as a clinical psychologist make you better? True or false? Turns out, based on data, it's false also. Despite the number of years of experience a clinical psychologist had, their ability on average was no better at judging these things. Many clinical psychologists and forensic psychologists believed that they had these subjective abilities, that they became enhanced, but when they looked at people's ability to actually predict these things, they got no better with experience. True or false? A professional clinical psychologist is better off to ignore their own judgment and intuition in both diagnosing disorders and predicting future behavior, like suicidal and criminal behavior, and instead rely on statistical information and more objective psychological testing. This one's true. I'm trying to illustrate why you should care a lot about research methods and statistics, and this class too, because it kind of combines those two things. If people ignore their own judgment, what they think might be some great personal ability to judge this, whether someone has some disorder or to predict some future behavior, and just rely on stuff that has been empirically, scientifically shown to predict things, that actually does better than relying on one's own subjective judgment. True or false? Extensive years of clinical experience and the level of graduate training. For example, a bachelor's student compared to a master's, and a master's compared to some kind of doctorate, PhD or PsyD. In other words, having more graduate training and more clinical experience, does that improve one's effectiveness as a psychotherapist? True or false? Turns out the answer here is false. That should be shocking to a lot of people, I think. What this is suggesting is that just with a bachelor's degree, in one sense at least, you're just as good of a therapist now as you will be if you go on to get a master's or PhD. You're already as good of a psychotherapist as you're going to be based on this evidence. Now, I should point out that you do need some minimal introduction to certain types of therapies to be the best therapist you're going to be. But extensive years of training, extensive graduate training, that seems to help absolutely none above and beyond a minimal introduction to something like cognitive therapy. I don't say this to dissuade you from going to graduate school. There's certainly good reasons to do that. For example, being licensed to do therapy, things like this. But the point here is that research methods matter. If someone says they're relying just on their clinical intuition or clinical experience, I suggest you run, because what they're saying isn't backed up by solid scientific or empirical evidence. So I went through that to try to illustrate why we need good methods and measures in the helping professions of psychology, in clinical psychology, forensic psychology, and in counseling psychology. And I'm going to read this whole thing to you. This is just taken really from an intro psych textbook mostly. The fact that a person has an advanced degree in psychology, such as a master's or PhD, it turns out is no indication that he or she can understand you better than you can understand yourself, or that he or she is in a position to advise you in how to solve your personal problems. For example, Robin Dawes, he wrote a book called House of Cards. I believe the subtitle was Psychotherapy Built on Myth, something like that, but it's definitely House of Cards. Robin Dawes reviewed the scientific evidence for the effectiveness of psychotherapy, which he concluded does have beneficial effects based on the evidence, by the way. Dawes wrote that, quote, all of the evidence indicates that, quote, the training, credentials, and experience of psychotherapists are irrelevant to the effectiveness of psychotherapy. Expert opinions often differ, just as any other educated opinions may differ. This is because expert opinions may or may not be based on evidence found through systematic scientific research. When expert opinion is based solidly on research, scientific research, it ceases to be mere opinion as evidenced by its increased predictive ability. If it's tested out scientifically, it's showing increased predictive ability. Thus, understanding scientific research methods, I'm arguing, are absolutely essential to someone who wants to be in clinical psychology. In fact, Keith Stanovich, in his book, How to Think Straight About Psychology, argues that if psychology is not scientifically based, and he's including clinical psychology, all the interventions we come up with, all the therapies we come up with, if it's not scientifically based, then it might as well not exist. That's the only reason we have psychology as a field. It's the only field that claims to study all of human behavior in a scientific way. So back to the research process. We've talked about initial observation, generating a causal explanation, a causal theory to explain those observations, logically deriving specific hypotheses, specific predictions to test. Now we're talking about going out and actually testing them. collecting data to see whether your prediction is correct. To do this, you need to define at least a couple variables to go out and test it, the variables that are relevant to testing your hypothesis. And you need to be able to assign numbers to those variables. In other words, you need to be able to measure those variables. A variable is a characteristic or a condition that can vary, for lack of a better way. It can have different values. Anything that can vary. Another way to put it is that a variable is anything that can be measured or manipulated, causally manipulated, and can differ, it can vary, across time, across participants, or across situations on different occasions. So you need to be able to measure a variable if you're going to quantitatively analyze it. Here, when I say to measure, I mean you're going to have to be able to assign numbers that represent something else. Those numbers, though assigning those numbers is the act of measurement. Those numbers are meant to represent the observations that you make. If you're going to validly test your idea, those numbers that you assign have to accurately represent the thing that they're meant to represent. If they don't, to a large degree, you're not actually testing your idea. That's extremely bad because maybe your theory's right, maybe your idea is exactly right, but if your measure sucks, if your numbers don't accurately represent what they're meant to represent, you're not actually even testing it. So you might draw invalid conclusions even though your theory is right. The data might say that your theory is wrong when it's actually right. So things like, with the mole rat example, we might measure length of time showing that aggressive stance that you saw on a previous slide. The number of aggressive stances they show, or the frequency in a certain period of time. The frequency of aggressive stances when presented with another mole rat. The last step in the research process is to statistically analyze those resulting numbers that you get. So here you're looking at actual results based on the mole rats, testing those two predictions that I told you about. They're using statistical analysis to find out if there is a reliable, meaning a consistent and repeatable, a reliable relationship in your study, and also how large is it. So we have divided between the green and the orange rectangles here, the arid or dry environments and the mesic or moist environments. So the arid environments are the resource scarce environments. The mesic are the resource rich environments, because how much rain they get, how dry it is, decreases the food resources for these guys. So you can see across the board, whether it's male versus male, male versus female, or female versus female, there's more xenophobia, more aggression where the resources are scarce in the dry environments. So that's a confirmation of the first prediction. Remember, the first prediction was that based on the theory that xenophobia is about protecting valuable resources like food resources, there's going to be more xenophobia where resources are scarce, because they're even more important there. Therefore, xenophobia is a more adaptive behavior where resources are scarce. Second prediction was that there's going to be decreased xenophobia when it's an opposite sex encounter. And you can clearly see that is the case. When it was male versus female, there was less xenophobia, presumably because they wanted to mate with them, might potentially want to mate with them. Because the opposite sex is not just a threat to your resources, they themselves are a potential resource. They represent an opportunity, not just a threat. So both predictions, both hypotheses were confirmed. But you might notice something weird about this study. It's a well-done study, although just what you're seeing on this slide, you might not actually know how well of a study it was done. That's because nowhere on that slide did I present the other stuff that they did. Control conditions. In any kind of good true experiment or any kind of quasi-experiment or experiment, you need a good control condition to compare to your condition of interest, your experimental condition. In the control condition, in the experiment we just talked about, common mole rats were presented not with a stranger, so every interaction you're seeing here was based on strangers. In the control condition, they were presented with non-strangers, familiar individuals that I guess they knew. They don't talk much, so we can't ask them, but they were familiar with them. They'd been exposed to them before, so they're non-strangers. The aggression was no higher among the mole rats from the dry environments when it was a non-stranger. So it very much looks like it's something about the stranger, those that they were not familiar with, that's setting off this aggression. That's why it's called xenophobia and not just aggression. It's specific to when it's a stranger. It's something about the strangers that seems to elicit the increased aggression, particularly in those dry environments and when it's a member of the same sex. Why is a control condition like this so important to test out an idea well? Without these control conditions, I wouldn't be that convinced by the evidence you saw on the previous slide, even though it looked like an interesting pattern. The reason you need a control condition is that if you're doing a true experiment, if you're doing an experiment, you absolutely, the number one thing you should be concerned about when you're thinking, is this a good experiment? Is this a well-done experiment? The number one thing you should be thinking is, are there any confounds? Are there any confounded variables? Are there any confound variables? So you need a control condition to compare. John Stuart Mill called true experiments, he called it the method of difference back in 1865. The whole point of doing a true experiment is that you, the researcher, are trying to set up a perfect situation where you have changed just one thing between your two conditions, between your experimental condition and your control condition. If, and it's a big if you set it up just right, so that there is just one difference on average between your two conditions, and if you see a difference in the behavior you're measuring between your two conditions, like in the mole rats, they were measuring aggression. If there's just one difference between your two conditions, and if you see a difference in the behavior you're measuring, then you can logically conclude that it was caused by just that one thing that you changed between the two conditions, just that one difference. But if there's a confound, that means that there's some other thing that was different between your two conditions. Maybe you didn't even know what it was. Maybe you didn't even realize it was a second change you made. You may have tried to just change one thing, make one thing different between the two conditions, but maybe you didn't get it right. Maybe you failed. Confounds can be very hard to spot, but they are the most important thing for judging whether a true experiment is a good experiment or not. So in a control condition, the proposed cause is absent. In your experimental condition, the proposed cause is present. So an effect should be present when the cause is present, and when the cause is absent, the effect should be absent, or at least decreased. That's why it's so important to have a control condition. The whole point of a good experiment is to infer a causation. If you have confounds, you can't infer a causation. You're trying to rule out confounds when you design an experiment. That's something you'll need to think about when you design your own experiment later in the class. And when you're writing up your paper, be thinking about, were there any confounds? To take another example of an experiment where people actually did test this idea, believe it or not, Andy Field gives us an example of a study that tested the hypothesis that Coca-Cola kills sperm, where they used Coke. They used old Coke versus new Coke versus Diet Coke, and I think maybe some other things, as a spermicide to see if Coca-Cola was an effective contraceptive. By the way, the bottom line is don't try that at home. There's certainly reason to be skeptical of the claims in that paper. So notice that hypothesis, it's a very good, clear hypothesis. Maybe a weird one, but it has a clear proposed cause and proposed effect. When it comes to writing your APA papers later, you're going to have to be describing the background theory for why you did the experiment that you did. And when you do that, the simpler the better, as long as you're being accurate in terms of explaining the hypothesis that you're testing. So Coca-Cola, the hypothesis here was that Coca-Cola would kill sperm. Simple hypothesis. It has the proposed cause, or more generally, we might say it has the proposed predictor variable, and it has the proposed effect, or more generally, we might say proposed outcome variable. So I say predictor and outcome variable because really those two terms are really always accurate. Whereas the more commonly used independent variable and dependent variable, those terms, they really only apply to true experiments. Sometimes I see in published papers actually, and it just pisses me off, I see people talking about independent variables and dependent variables with a correlational study, and there is no independent variable or dependent variable in a correlational study, but there is a predictor variable and an outcome variable in those studies. So really the more general terms are predictor variable and outcome variable, or sometimes criterion variable. Independent variable is a specific type of predictor variable, and a dependent variable is a specific type of outcome variable. Those terms only apply when you have a true experiment where you've manipulated a variable and you have control over other things. Since this class is experimental psychology, we're essentially always going to have an independent variable and dependent variable, although we will allow some quasi-experiments, and strictly speaking, those aren't really true independent variables either. So an independent variable, it's the proposed cause in an experiment. It's also one type of predictor variable because you're going to be using it to predict the outcome variable. By definition, an independent variable is one that's being changed by the researcher intentionally. It's being manipulated by the researcher in an experiment. So in our example, what variable is the independent variable? It's the Coca-Cola, the application of Coca-Cola as a contraceptive. So the Coca-Cola itself is the independent variable here. Either they applied Coke or Diet Coke, for example. The dependent variable is the proposed effect in an experiment, or it's one type of outcome variable, the thing that you're trying to predict with the thing you manipulate, the thing that you're trying to affect, the proposed effect. It is a measured variable. You certainly need a measure of it if you're going to test out your hypothesis, but you don't directly manipulate it. You, the researcher, directly tinker with the independent variable, and you're seeing if that has an effect on the dependent variable. So a dependent variable is measured, not manipulated, not directly in experiments, not manipulated directly by the researcher. So in our simple example here, sperm is, number of sperm, I would say, is the dependent variable because you're trying to see if it was affected by the application of Coke versus other drinks, for example. So believe it or not, Ampere et al. Back in 1985 actually tested this hypothesis, tested the idea, and what they found was that Coke was an effective spermicide, that it affected sperm motility. Original Coke was 5 times more effective than new Coke, and Diet Coke was actually most effective as an after-sex spermicide. Again, I'm absolutely not advocating this. Don't try this at home. There's certainly reason to be skeptical. Other researchers actually tried to verify these results. This study's been done not just once, but at least a couple times. And if you read that Snopes article and your link in your slides, I'm not going to show it to you now, but if you want to, if you're curious about such things, they report that other people were unable to verify those results. So sperm doesn't look like it's actually an effective spermicide. Okay, some important things in thinking about statistics. Really, they're some of the first things you probably learned in a statistics class, whether it was Math 1200 or in psychological statistics like 3001. You got to know the difference between a categorical variable and a continuous variable, and I think it's simple enough once you get the hang of it. But it's really important. Some statistical programs like SPSS, it's really on you, the researcher. You've got to know what kind of variable you have, and that's going to change what kind of statistics are appropriate to use in some situations at least. So a categorical variable, well, it's something the numbers represent categories. You can't be a little bit of the category. You either are in the category or you're not. So most simple example I would say is probably male, female. Now, of course, some of you will object and say that there's in-between cases. Certainly there are, but actually, even those in-between cases would usually be statistically coded as some other category, maybe a number of 3 instead of a 1 or a 2, or a 0 and a 1. So male and a female. If I was going to do a study where I was looking at a sex difference on some psychological trait, well, I'd have to assign numbers to sex in order to analyze those results. So it doesn't actually matter with a categorical variable like this, a nominal variable. It doesn't actually matter what numbers I choose to represent it. If I was doing male and female, I would just choose 0 and 1. But I could have chosen 1 and 2, or I could have chosen 500 and 3,837. It doesn't actually matter what numbers you're using, because those numbers, they don't represent a real value or an amount of something. They just represent that this individual was in this category, so that number is just a category, and this other individual was in this other category. So the numbers just represent categories. They don't actually mean anything in terms of one having more of this trait or anything like that. It's just a category. That's what a nominal variable is. So if you're going to indicate the species of a subject, whether they were a human or a cat or a bat, you almost certainly use a nominal variable. You're probably not going to have a Batman or a Catwoman so that they didn't fit into a nice neat category. So you probably just have a nominal variable here. Also, ordinal, we'll talk more about it in a second. But in some ways you could call ordinal a categorical variable. Well, in some ways it doesn't really feel like a categorical variable. But that's where you're using numbers that represent a particular order to something. So I think the classic, most simple example is using numbers for the order of finish in a race. If you held a race around a track and you just noted who came in first place, second place, third place, etc., and you actually just used those numbers, first, second, third, 1, 2, 3, to represent the order in which they finished, that would be an ordinal variable. The numbers do represent categories in a real sense. First place, second place, that's being considered a category here, but they have a natural order. So there, the numbers that you use do actually matter. With nominal, the numbers just represent a category with no order, so it doesn't matter what numbers you use. With ordinal, it's in the numbers you use does matter. And then there's 2 types of continuous variables that actually, for our purposes in psychology, you really don't need to distinguish between interval and ratio. Just know that they're considered continuous. Here, the numbers that are used, they don't represent categories, they represent an amount of something, a value of something. So a reaction time. If you were a cognitive psychologist and you gave people some kind of memory test where you measured reaction time for how quickly they remembered something, maybe. That reaction time measure would be a continuous variable because how fast they respond varies on a scale, and you'd be using the number for that continuous number. And actually, that'd be a ratio example because a reaction time has a true 0 point. 0 would be no time at all. So in statistics, probably both in Math 1200 and in psychological statistics, you should have learned about what I was just talking about, these different levels of measurement. Remember, we've defined measurement as assigning numbers to represent something, basically. Because in the end, after you do an experiment or a correlational study or a quasi-experiment, all you're really going to have is a spreadsheet of numbers that are meant to represent variables. And there's different ways that those numbers can represent the variables. They could be categorical. The numbers could represent categories, or the numbers could be a continuous amount of something. So this is just more detail actually about the previous slide. So categorical, for our purposes, actually, I don't think you need to distinguish between a binary variable and a nominal variable. The only difference between them is that a binary variable, it's a nominal variable with only two categories. A nominal variable can have more than two categories. So if you just had male, female, that would be binary, but it's also considered nominal. Someone's either dead or still alive, that would be binary. Pregnant or not, that would be binary. If you use numbers to represent those things, again, it wouldn't actually matter what numbers you used, just the different numbers would just represent those categories, the category of dead versus alive, or pregnant or not. If you're using the numbers to represent that, that would be binary or nominal. Nominal is the exact same thing, except you can have more than two categories. So if you were going to classify people in terms of things that they ate, whether someone was an omnivore, meaning they ate meat and fruits and vegetables, everything, like most humans, or a different category, vegetarian, only eating veggies and fruits, or a vegan, kind of like a vegetarian, except they don't eat anything that comes from an animal, so like no milk, or a fruitarian, I guess someone that only eats fruit. You could have as many categories as you want. As long as the point is that as long as the numbers just represent a category and the numbers don't represent an actual value, then it's a categorical variable like this. And in the way I've been describing it, it's nominal. Ordinal, as I said before, the classic example is the order of finish in a race. It's kind of the same idea as a nominal variable, but here the numbers represent the numbers that are used to represent things have a logical ordering to them. They have a rank order. So the values that you use actually do matter for the ordinal ones. You couldn't just use any old number because they represent an order. But they're still categorical. So whether people got a fail, a pass, or some kind of pass with high distinction or something, that could be a three-category thing where you have three numbers to represent those three categories, except you can't just use any old numbers because they represent, there's a natural ordering to them. Next is the other types are continuous. Both interval variables and ratio variables are continuous variables, and you could basically get any value on a continuous scale. So an interval variable, it's called an interval because there are equal intervals on the variable, and they're meant to represent equal differences in the underlying thing that you're trying to measure, the underlying property that's being measured. So for example, the difference between a 6 and an 8 on an interval scale should be equivalent to the difference between a 13 and a 15. There's a lot of things but most things in psychology are usually assumed to be interval. Consider like a self-report questionnaire of how happy are you on a scale of, let's say, 1 to 5. 5 being extremely happy, very happy, 1 being very sad or something like that. So it's assumed that the difference between a 1 and a 2 represents the same difference in happiness as the difference between a 4 and a 5. And that certainly may not exactly be the case, and there's good reason to think that it's not exactly the case. But typically, things in psychology are assumed to be measured on an interval scale like that. A lot of things that we measure, at least. Things on those self-report questionnaires, typically. So with interval, it's a numeric value that differs, and what differences between values correspond to differences in the underlying thing being measured. or at least it's assumed to be tied to that. So a continuous scale of how much pain are you feeling, pain level, how much stress are you feeling, a stress level. Some of these things might not be self-reported. They might be based on like amount of cortisol in the blood, for example, to measure stress level. Ratings of mood, age. Age is continuous. You could, from birth to death, you're continually aging. Sorry. The big thing that distinguishes between interval variables and ratio variables is that a ratio variable has a true 0 point, whereas 0 on the scale really means none of the underlying property being measured. So I gave the example of reaction time earlier. Time is a good example of something that there is the 0 point on a time scale means no time at all, no time passed. So that would be ratio. There aren't that many ratio things in psychology. Most of the measures we've come up with don't have a true 0 point. So for example, on an IQ test, if you get all the questions wrong and scored a 0 on an IQ test, presumably that doesn't mean that you have absolutely none of the property of intelligence. Presumably there's some on there you couldn't even take in the test. So ratio is going to be it's the same idea as the interval scale, but with ratio, the ratios of score on the scale also make sense because there's a true 0 point. With interval, there's no true 0 point. So a score of 16 on an anxiety scale means that the person is in reality twice as anxious as someone scoring an 8, if that were a ratio scale. Height would be an example of ratio, because even though no one is of 0 height, the measure has a true 0 point where there could be something that has no height. Or 0 weight, same idea. A Kelvin scale for measuring temperature. So 0 degrees Fahrenheit, 0 on Fahrenheit doesn't mean the absence of all heat. But 0 degrees Kelvin does mean the absence of all heat. So 0K, also known as absolute zero, where particles stop moving, hence no heat, so it has a true 0 point. Again, for psychology, at least currently, it's not terribly important, I don't think, for you to be able to distinguish that easily between interval and ratio, because the statistics that we use don't really distinguish. They just treat them both as continuous. So you definitely, to really understand how to analyze data, you got to know the difference between nominal, ordinal, and continuous, including both interval and ratio. It's good to be able to recognize examples of that. Another thing that you definitely should have gotten from various classes that you should have already taken are the notions of reliability and validity of measures. There's other types of validity that we're not really going to get into right now. So one of these is measuring consistently or repeatedly. Which one is it? Is it reliability or is it validity? That one's reliability. And I guess for me, the easy way to remember it is that reliability starts with an RE and repeatability starts with an RE. So if I step on a scale to weigh myself today, and it says I weigh 195, and then I step on a scale tomorrow, and it says I weigh 215, and then I step on a scale the next day, and it says I weigh 154, is that scale reliable? Absolutely not. It's not consistently measuring it. Presumably I can't gain that much weight and then lose that much weight over the course of a day. That would be more than a little unhealthy, and actually, even if you just didn't eat at all, you wouldn't be losing that much weight in one day. So not a reliable measure if the scale was telling you that. Validity is, are you really measuring what you're trying to measure? You're really measuring the underlying thing that you're trying to measure. So is an IQ test really measuring whatever intelligence really is. And we could get into all sorts of talk about the trouble with even talking about that necessarily. I think maybe more importantly, is it measuring something useful to call that? Is a happiness measure really measuring underlying happiness, underlying satisfaction? The thing that you're trying to measure, is your measure really validly tapping into what you think you're measuring? So it's actually really straightforward. We can quantitatively measure how reliable a measure is. There's different types of reliability. There's test-retest reliability. That's the one I was describing with the scale that I stepped on to day 1, to day 2, to day 3, and I said it's not reliable at all. We could actually assess how reliable. It might be 0. There's also, depending on what kind of measures you have, there might be inter-item reliability. That's consistency or repeatability across different items, usually going to be self-report items. So if you had a 10-item questionnaire where all the questions related to how happy someone was, well, all 10 of those questions should tend to be consistent with each other. They should tend to repeatedly measure the same underlying thing, at least to a degree. And we can easily assess that, give it a quantitative amount to how reliable it is. So reliability is quite easy to assess. Validity, on the other hand, can be trickier, because how do we assess whether we're really measuring the thing that we want to measure? You can actually quantify that in a certain sense, but it's certainly trickier. Thinking about my example with the scale, if I step on the scale today and it says I weigh 195 pounds, the next day I step on the scale and it says I weigh 215, and then the next day I step on the scale and it says I weigh 154 pounds. We've said it's unreliable. Is it a valid measure of weight? If it's unreliable like that, and it's meant to measure something that's supposed to be relatively stable like weight, then no, it's not valid either. So if, and it's a big if you're trying to measure something that's relatively stable, like a stable personality trait, like extroversion based on evidence, it's not immutable totally, but it's a relatively stable trait. It doesn't usually change radically, so it's a relatively stable trait. If you have a measure that's unreliable and it's meant to measure something stable over time, then it actually can't be valid either. But something could be reliable but not valid. So for example, if I had a measure, if I thought for some weird reason that if I measured the length of your big toe, it was a measure of intelligence, and I measured your big toe today, and then I came back and measured your big toe again tomorrow, would I get consistent results? Yes, I would. If I measured the length of your toe today and measured the length of your toe tomorrow, I'd get approximately the same answer. So it would be a reliable measure. And if I thought it was a measure of intelligence, I might interpret that as it's a reliable measure of intelligence. But is it a valid measure of intelligence? Well, no, it certainly wouldn't seem to be. I have no reason to think that the length of your big toe correlates with real intelligence. So the big question is, well, then how do we show that something's valid? And there's definitely different types of validity, and showing that it's really measuring what it's supposed to measure. But really, those different types of validity really boil down to this. Does this measure predict or correlate with, does it correlate with things that we would expect it to correlate or correlate with if it were measuring what we intended it to? So we can't just say, oh, it looks like a measure to me. It looks like a valid measure to me. We can't just say, well, big toe seems like intelligence to me. Because if you invented some measure, you're probably always going to think that. So face validity is actually kind of a silly way to assess validity. It's just kind of your intuition. Does it seem right? There's no real objective or systematic way to assess it there. The way to more objectively measure or to assess, is this measure a valid measure? It's not impossible. The question is, does this measure accurately predict things we would expect it to? For example, the big 5 personality traits. Even though there's a lot of people just want to dismiss self-report out of hand, well, those self-report measures have been shown to have some validity because they predict things that you would expect them to predict if they were good measures, were valid measures. We're actually measuring the thing they're supposed to. So, for example, some studies have shown that conscientiousness predicts how faithful someone is to their spouse. Just because you score high on conscientiousness doesn't mean you're going to be faithful to your spouse. But it predicts it to some degree. It correlates with it. That's evidence that a self-report measure of conscientiousness has some validity. To some degree, it looks like it is measuring real conscientiousness, whatever that is. Self-reported openness to experience has been shown to predict how likely you are to change your job. Being open to change, open to new jobs, that's something you would expect it to predict. So self-reported openness seems to be tapping in to real underlying openness. Self-reported extroversion. Self-reported extroverts look people in the eye more, and they tend to have more sexual partners. Things you would expect it to predict. IQ scores. Despite all the bashing that they get, we actually have more evidence for the validity of IQ tests in predicting things than many things in psychology, I would say. IQ scores predict GPA in the future, so if you take an IQ score now and then go to grad school or really undergrad, it tends to predict your GPA. Does it predict it perfectly? Well, definitely not. But does it tend to predict it? And the answer is yes. Supervisor ratings of job performance. IQ tests have been shown to predict that to some degree. Advancement within your field. So once you get there, does IQ predict how far you advance within your field? It does seem to. It predicts some health outcomes, relatedly death. High IQ people tend to live longer, a little bit. High IQ people tend to be less likely to be convicted of crimes, at least. And there's maybe a little iffiness there because maybe they're less likely to get caught. I don't know. Amount of time needed to think about a simple cognitive reaction task. High IQ people have a quicker cognitive reaction time, basically. So I'm going to show you a clip now because I don't really want to talk too much more about this. This clip is just meant to talk about this idea of validity, mostly of self-report stuff and IQ tests. And he's going to say some of the same things I've already said. This is going to be Paul Bloom from Yale University. He's just talking to his intro psych class about how we know that measures are measuring accurately, that they're measuring what they're meant to measure validly.